Welcome to the second part of the integration tutorial showing how to integrate the Virgo use case using itwinai. So, in the first part of the video, we show how to understand the use case code and how to rearrange it in an itwinai sequential workflow. So we copied the code and rearranged it using itwinai components. The way we organized it is that we copied helper functions under the SRC folder. So we have dataset creation, helper functions, we have machine learning models, like different versions of the decoder, some utility functions. This is use case provided code, and it will remain in the SRC folder. But then we also defined some workflow steps represented as Python classes of different types. So we have a time series data set generator of type data getter, and its execute method receives nothing and returns a dataset, in this case a data frame. The data frame will be passed to the second step, which is the time series dataset splitter of type data splitter. And its execute method, in fact, will receive a dataset as input, and then it will return 3 items as output, 1, 2, and 3. These 3 items will be passed to the next step, which is the time series processor of type data processor, which receives 3 items as input and returns 3 items as output. So as you can see in the return case. Very well. So now the dataset is generated, split, and preprocessed. So we can move to the trainer. So in the case of the trainer, again, we have an execute method, which is not shown here because it's we are using the execute method from the torch trainer. And the execute method of the torch trainer receives again 3 items as input, the ones returned by the dataset preprocessor, and that's it. So for the Virgo trainer, we are implementing this noise generator trainer class of type torch trainer, which allows us to reuse most of the logic provided by the torch trainer. In this case, the users just need to override this create model loss optimizer, so this method that in fact creates a torch model, in this case using a switch case, a loss criterion, an optimizer, and then, as an important step here, the model and optimizer are distributed when we are using a distributed strategy. So reusing the torch trainer class, the use case can already access distributed machine learning out of the box just by adding this code block after having created the model. Again, the use case will also reuse the train function, overriding the train function provided by the torch trainer. So that this train function is defined by the use case, and during the integration we adapted this function a little bit to make it suitable for distributed machine learning. So first important thing is that epoch goes from 0 to number of epochs minus 1, and at the beginning of each epoch we need to set the epoch using the set epoch from the torch trainer class. This is an important step. And then we remove the prints and we replace them with the log. So again, we can reuse the log method provided by the torch trainer, which allows us to log in an easy way metrics given their value, their name, their kind, so in this case a metric, a step, so the step should be incremental, In this case, with this formula, we're computing an incremental step for to store epoch loss batch across all epochs, and a batch ID. Similarly for the validation loss batch. So the validation loss batch and the epoch loss batch are the values, they store the value of the loss on each data batch sampled from the data loader. However, we can also have an overview on the whole epoch, and this can be done computing the epoch loss and validation loss. So epoch loss and validation loss are nothing more than just the average of the losses of each batch. And usually this metric give a bit more generic, general overview of how the training is going, is less noisy, and usually is preferred. However, if the users would like to know it, we can also give more granularity and provide more granularity and log the loss obtained computed on each batch. Another important concept is that when we want to print or do something which may result in a race condition, in this case the print is not, but imagine saving to disk, writing to a file or something like that. We want to make sure that this operation is done only in one worker in the multi-worker context. And so we can reuse the set.strategy.isMainWorker flag, which will allow us to perform this operation, in this case a print, only in a single worker in the distributed context. Yeah, I already explained this in the previous video, but just to recap briefly, again, when we are in a distributed context, each worker is trained on a subset of the dataset, which means that the validation loss, for instance, in each worker is different. So if we want to have a general overview of how the validation loss is going during training, we need to gather the validation loss from all the workers. And this is exactly what we're doing. So this way, with gather object, we're gathering this object from all the workers. So this will be a list. So we take the average of this list and we get the global average loss. And then if the global average loss, which is the validation loss, has improved, then we can save the best model, and we can save a checkpoint as well. So yeah, this is pretty much the same logic that we already saw in the previous tutorial, maybe in more details. So to recap, the workflow is divided in the following steps. We have a dataset generator, dataset splitter, a dataset preprocessor, and a trainer. So the difference now is that, as you can see, we also have a weights and biases logger, because now we're going to see how weights and biases can be used to log. Another difference is that now we're using a smaller generator, because given that the dataset is smaller, we can appreciate better the evolution of training, and we can avoid overfitting. So first of all, let's log in into weights and biases. So I'm already logged in. If you're not, you can log in, and this will request a secret token that you can obtain from your weights and biases profile. So since everything is already set up, we can start training. So we don't need to use a train script actually. Since the whole workflow is described in this configuration file, the nice feature of itwinai is that we don't need additional logic to execute this workflow. We can just use it. We can just run it just by using this configuration file. And to do this, we will say itwinai exec pipeline, and then we will tell what is the configuration, and then we will tell it that it should run. the pipeline named training pipeline. So if we run it like this, it will run each step from the first to the last, which is fine. But since the dataset generator step is a bit time consuming, I already ran this before and I don't want to generate the dataset again. So I want to cache this step and start the execution from the second step of the pipeline. So yeah, like in a cooking tutorial, I pre-cooked the dataset so we can just reuse it from now. So I will just say, let's start from the first step, from the step of index 1, so which is the dataset splitter. And let's run the pipeline from the second step on. Okay, small typo, of course, why not? So now we wait a little bit and the training has started. So as you can see, we can already see some weights and biases information, which is telling us that it's going to save our logs to weights and biases.ai. Matboon is my project, default experiment, and the run will be this one. So we can already see the run if we open it. Let's open it. So this is the new run. Let's give it some time to load. And yeah, so as we can see, this is currently running. So not all the plots are complete, of course, it just started. But the nice thing of weights and biases is that this is saved on weights and biases cloud. So we don't need to host any weights and biases server if we don't want to. And we can access this dashboard from wherever we want. So yeah, nice. So the training is finished. So as we can see, we have more plots now. Let's refresh the page. So now we just executed the training for 2 epochs. So therefore, as you can see, the plots are very, very simple. So let's move to a longer training that, again, it was pre-cooked. So here we trained for 50 epochs, if I remember. And yeah, so in this case, we can compare the different metrics. But also the nice feature of weights and biases is that it will give us information about system metrics without us having to explicitly request for that. So we can see disk utilization, disk I/O, process memory utilized by our training algorithm. So now it's very small. Of course, it's just a toy. We can visualize CPU utilization and so on and so forth. Also network traffic was here. So at the moment I'm training on a CPU system, but if I had a GPU, I would also get GPU utilization information, which is very, very interesting. And also I would get GPU power usage, so how much power of the GPU was used during training. Very, very useful metrics. But as we saw before, we're not using only a weights and biases logger, we're also using an MLflow logger. So MLflow logs will be stored locally unless we specify it in a different way. So what we can do is we can run the MLflow UI with the backend store URI flag and passing as the location of the backend store URI the MLlogs MLflow, which is the default location at which the MLflow logs will be stored, which is inside this folder, MLflow here. So if we run this MLflow UI from VS Code, VS Code is already tunneling over SSH, so we can open in the browser. And we can also access the MLflow UI, which is pretty much the same as the MLflow server. And again, we can see all the runs. Let's see a run which was a bit longer. So again, we can see the different metrics. We can see, for instance, this is the train loss, the validation loss. So as we can see, the model is overfitting, but it's okay. I mean, the dataset is very small, and we can see the artifacts. So these are the checkpoints of the model, which were done at each epoch. We can change this. And we can also see the best model. So the model that was saved when the validation loss was the lowest. And yeah, so with this, we have seen how to track the training of a machine learning model using different loggers, so weights and biases, and MLflow. And the important aspect of this is that the user didn't have to do much. The only thing that the user had to do to have access to all of these loggers was first implement a trainer class which extends the torch trainer, use the self.log method, explicitly saying when he wants to log a metric or when he wants to log an artifact. Other kinds are available, and you can find them in the documentation. And the third ingredient for this was going into the configuration and specify MLflow logger and weights and biases logger as loggers used by the torch trainer. So how is it possible to use multiple loggers? First of all, you're not forced to use multiple loggers. You can use also only one. So inside the constructor arguments of the trainer, so this is our noise generator trainer. These are the constructor arguments. We have the logger key. So for the logger field, you can specify just one of these. But if you want to use multiple loggers at the same time, which is totally fine, you can use the itwinai loggers collection. So this is already provided by itwinai, and this loggers collection is a wrapper that allows to specify a list of loggers that should be used together. Now, a small comment on this. The more loggers we have, the more overhead we have during training. So it's good from a functionalities point of view. We have more functionalities, more features, but we may want to adjust the login frequency, which means how often should the logger actually log and save and store to disk or send the results over the network. So when we, again, the explanation of this field can be found in the itwinai documentation. But briefly, if we want, so when we give batch, this means that every time we call the log function, the logger will actually log. If we give a number, this means that the logger will log once every 100 calls to the log. We can also give epoch, which means that it will only log at the end of it will only log epoch metrics, epoch items, and not batch items anymore. So as you remember, we were having two different metrics here that we're logging. So we were logging the validation loss batch, for instance, and the validation loss. So this is computed for each batch, this is computed for each epoch. So we can force the loggers to log only this only at the end of the epoch, and the logger will understand when we are at the end of the epoch because we are not giving a batch ID. If we give a batch ID, then the logger will assume that we are that what we are logging is the result is a metric computed on top of, starting from a batch. If we don't give a batch ID, like here, we don't give it, The logger will assume that we are outside of the inner loop of in the data loader, and it will assume that then we are logging at epoch level, and so it will always log basically. And with this, we've seen how to use weights and biases, ML flow, and actually there is also another logger which is just for debugging purposes, which is the console logger, which just prints to the standard output what you log. And when you save an artifact, it will save it to disk under ML logs, simple logger. And that's it.